Chapter 11. Chapter 11 is not a whole lot there. So it's going to take just a little bit of time to go over some of the concepts of Chapter 11. And then you guys can take a look at it and do some of the problems. Don't worry about doing freezing point and boiling point elevation problems at the end. I'm not concerned with that. And we're going to go ahead and take a look at it. Most of this we've actually already covered, but I'm going to go ahead and just review some of the concepts again because I don't think everybody was here for the class when we talked about polar and non-polar. If you recall, polar, we're talking about solvents, polar solvent versus a non-polar solvent. What makes something polar is it's a molecule, a molecule whose atoms do not share electrons equally. Alright, so what this does is, I'll draw you a picture here. So let's take a look at CH3F. Alright, what does this molecule look like? Well, you've got carbon in the middle with 1, 2, 3 hydrogens. I'm not going to worry about the 3D representation of it. I'm just going to give it to you kind of real quickly. So, in the ideal world, all these atoms come together to form methylfluoride. What would this thing be called? I can't remember what it's called. Don't worry about it. You don't need it. But all these, in the ideal world, all these atoms would be around this carbon, and they would all share electrons equally, right? Because they all have 2 bonds, right? 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons here. Actually, this has more than 2 electrons because fluorine has all these guys too, right? But all these electrons would be shared. Well, we know we're not living in the ideal world anymore, right? So, because it's not an ideal world, what is fluorine? Fluorine happens to be the most electronegative atom on the planet. Fluorine is very, very greedy for electrons. It wants to steal electrons. It is the master pickpocket of the electron world because it greedily desires electrons so much, that it's going to pull some of these electrons toward itself, right? So normally, you expect all these electrons sort of be happy orbiting around each of their atoms. But because fluorine is so hungry for electrons, that the majority of electrons spend their time around this side of the molecule, right? Because it spends most of its time around this side of the molecule, we call this molecule polar. Because it's polar, it has a dipole moment. A dipole moment meaning like a temporarily induced charge on this molecule because the electrons are spending more of their time around here. Right? More of their time around there. Because they're spending more of their time around here, we do this little symbol. And that little symbol shows you that this side of the molecule is a little more negative and this side of the molecule are a little more positive. Because that electron likes to hang around down here. This is a polar molecule. And we have another way of expressing that, and that's doing this little arrow thing here, which I really can't stand, but it's... And that little arrow thing means, it just points in the direction the electrons are most likely to go, right? So they point towards the fluorine saying, hey, fluorine is a really electronegative atom. The electrons are going to spend most of their time down here. So this would be an example of a polar molecule. Now, incidentally, I can have this. Look, CH, or carbon tetrafluoride, which would look like this. Fluorine, 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 fluorine. Now, this is actually nonpolar because each of these fluorines pull at the electrons on the carbon the exact same way, right? So think about it. You're sort of locked into. They're pulling. The carbon in the center is being pulled, but it's being pulled equally in all directions. It's being stretched equally in all directions. Because it's being stretched equally in all directions, there is no dipole moment for CF4. And we call this guy, he's nonpolar. And I think your book calls it purely covalent, it's got some sort of weird name for it. What the heck is it? Purely covalent bond. A purely covalent bond. Purely covalent. I don't understand. How do you have polar? Purely covalent is, I don't understand. But it's polar and non-polar. Alright, this has no dipole moment. This has a dipole moment. And if you recall, we also talked about that same day, we talked about how electrons, water. We said water was a very polar molecule, one of the most polar molecules out there, right? Because it has these unpaired electrons. These unpaired electrons really draw electrons towards themselves. Right? So this would be an example of another polar molecule. All right, so we said what were the things that create polarity? Polarity. Interesting. Yes, yeah, that would be a correct word to use. Polarity in a molecule. Unbonded, unpaired electrons cause polarity. Really electronegative atom causes polarity. All those things cause polarity in a molecule. As opposed to nonpolar. Nonpolar is a molecule whose atoms share electrons equally. And don't be fooled just because it has a highly electronegative atom in it. You got to see what that highly electronegative atom is doing. If there's 4 of them and they're all being pulled in the same direction, then it's all going to be a wash. And we said when we were talking about this for solvents, we said like dissolves like. So if I have a polar molecule, that polar molecule will be dissolved by a polar solvent. And we gave an example of a grass stain, right? Or actually, yeah, okay, no, let's use a fat stain. Someone got bacon grease on their blouse or on their shirt, right? Bacon grease. Now, I got bacon grease on me. Is water going to take it off? No, water is not going to take off bacon grease. Bacon grease is a fat. All right? And fats are non-polar. Basically, all a fat is a really long chain of carbons. Right? Around that long chain of carbons, you've got a bunch of hydrogens. Right? All these little things are hydrogens. Right? Really long chain, bunch of hydrogens, nothing polar about it at all. Right? Non-polar. I can't take my polar molecule. All right, here's my water. Very polar molecule. Oops, plus. Very polar molecule. I can't take my polar molecule and expect that to dissolve bacon grease because this is polar. You're probably not seeing this, are you? This is polar. You're just barely seeing it. So my water is polar, my bacon grease is non-polar. You ain't gonna get that fat stain off of your stain off? Well, gosh, how about a non-polar solvent? Yeah, non-polar solvent. What would be a great non-polar solvent? Oh, carbon tetrachloride. Look at that, carbon tet. Or, no one's carbon tetrachloride. No, that's not carbon tetrachloride. It's carbon tetrafluoride. Carbon tetrachloride looks like this. Hey, but you could use carbon tetrachloride too. That's also a non-polar solvent. Excellent non-polar solvent, by the way. This is a solvent that is often used in chemistry for using gas chromatographs to dissolve really large organic molecules, non-polar organic molecules, to dissolve them in order to do analyses of carbon tet. Or no one has carbon tetrachloride, no one has carbon tetrafluoride, but y'all do have gas. You said you get gas. Y'all have gasoline. How about gasoline? I don't know if you get gas or not. But you're all sick, so I don't know. Maybe you do have some gas. But if you get gasoline is another non-polar solvent. Gasoline, incidentally, is there's all sorts of crap in gasoline. Gasoline is a mixture. I think I've got a gas chromatograph of gasoline. There's actually a ton of stuff, and there's hexane. There's xylenes, toluene. There's just a ton of stuff in gas. But gasoline, for the most part, I'll say it's polar. But there are some polar stuff in gasoline. But I don't want to talk about that. How about diesel? Diesel, that's non-polar. All right, that's just a bunch of straight chain hydrocarbons. That's just a bunch of this stuff. Right? So diesel, gasoline, all these non-polar stuff would take out your grease stain. Water, not so much. The reason why, what does your moms and dads do, or maybe you do, what do your moms and dads do to remove stains from your clothing? Oh, they use a soap, right? Right. And what soap is it's a really long chain carbon. I'm really off subject. Long chain carbon, but on this long chain carbon, they'll throw like a hydroxyl group or a carbonic acid. Basically, it's a surfactant, right? And what this is you have this long chain non-polar molecule attached to this, which happens to be polar. Right? What this allows to happen is this polar part of this non-polar molecule will grab this grease stain and pull it out. Well, actually, this grabs the grease stain because this is non-polar. It grabs a hold of that, but this polar part then brings it into the water, right? Makes it water soluble. But I'm off track. But yeah, that was fun to learn about. All right, so I mentioned a couple of things that we need to talk about. I mentioned solvents, and I didn't mention solutes, but that's what we need to talk about. A solute is something that is being dissolved in a solvent. Right? So it's a substance that is being dissolved by the solvent. Right, so if I have a cup of water, there's my cup of water, and I'm going to add to my cup of water some salt. Right, here are my salt crystals. I'm going to throw them in there. So this is salt. If I can spell it, salt. My salt is the solute. My water is the solvent. Incidentally, will the salt be dissolved by the solvent? Well, the water is polar. What's salt? Is salt polar or non-polar? Is there a charge associated with my salt? Oh my gosh, you betcha. You betcha, it's a ionic bond, right? The ionic bonds screen polarity because they're charged. All right, now the last thing we need to talk about, can you believe it? We're already at the last thing we need to talk about, is things that affect solubility. Right, because we're now dissolving stuff, right? We're trying to dissolve stuff, and we want to learn what kind of things affect solubility. What affects, oh gosh, is it affects or affects? I don't know. What affects solubility? Solubility. What is solubility, first of all? Well, I skipped that, didn't I? I did. I skipped solubility. Well, let's define what solubility is first. Solubility is the measurement of the maximum amount of solute that can be dissolved by a solvent. Is measurement of the maximum amount of solute that can be dissolved by the solvent. Right, it's often given it's often defined as grams of solute divided by grams of solvent. All right, we just did salt, right, NaCl. Salt solubility, NaCl solubility is 37 grams per 100 grams of H2O. Right, so I can dissolve 37 grams of sodium chloride in 100 grams of water. And that's at standard temp and pressure. Standard, or STP is often what you see. STP, standard temperature and pressure. All right. Solubility is the measurement of the maximum amount of solute that can be dissolved by the solvent.